A is equal to 240 has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into two A is equal to 120 nuclei in a process called the nuclear fission, the nuclei get more tightly bound and hence become more stable in the process. This shows that a large amount of energy would be released in this process. This is the reason for the high energy release in nuclear fission. Similar is the situation when two very light nuclei with A around 10 join to form a heavier nucleus by a process called the nuclear fusion. The binding energy per nucleon of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a fusion process. Thus, we observe that for most of the nuclei, the binding energy per nucleon is very large compared to the binding energy of atoms in a molecule. For example, when two hydrogen nuclei, that is, protons, fuse together, a larger nucleus of deuterium is formed. In this process, a large amount of energy, approximately equal to 0.42 million electron volt, is released. Similarly, when two nuclei of deuterium fuse together to form a nucleus of helium, energy equal to 3.27 million electron volt is released in the process along with the neutron. Two nuclei of deuterium can also fuse together to form a nucleus of tritium, releasing an energy equal to 4.03 MeV along with a proton. In all these nuclear fusion processes, we see that two nuclei combine to form a heavier nucleus. Similar is the situation when two very light nuclei with A around 10 join to form a heavier nucleus by a process called the nuclear fusion. The binding energy per nucleon of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a fusion process. Thus, we observe that for most of the nuclei, the binding energy per nucleon is very large compared to the binding energy of atoms in a molecule. Thus, there should be a strong attractive force among the nucleons in the nucleus, which can bind the nucleons together in the tiny nuclear volume in spite of the Coulomb repulsive forces that exist between the positively charged protons. This force is called the nuclear force. From our analysis of the nuclei, we come to know some features of nuclear force. Nuclear force has to overcome the Coulomb force between protons and keep them together. So, nuclear force must be stronger than Coulomb force. As gravitational force is weaker than Coulomb force, we can conclude that nuclear force is stronger than both Coulomb and gravitational force. Therefore, nuclear forces are the strongest forces in nature. This can be observed from a graph of nuclear force versus distance between nucleons. Here is the graph showing a plot of potential energy between a pair of nucleons against their separation. It is observed that potential energy is the least for a distance r0 of about 0.8 Fermi. From the graph, we see that the potential energy is very high for r values less than 0.8 Fermi, which implies that the nuclear forces are very strong in that range. This force falls rapidly to zero as R value crosses 0.8 Fermi. Nuclear forces bind the nucleons together. That is, they exist between two protons, two neutrons, and also a proton and a neutron. Therefore, nuclear forces are independent of the charge and the nuclear force acting between two neutrons, or between two protons, or between a neutron and proton, is approximately equal in magnitude. We have simple mathematical equations representing the Coulomb force and the gravitational force, but we do not have any such mathematical expression for the nuclear force.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।